Hello once again, class, and welcome to another mock lecture. We're continuing on with the Math 111 prereq series. This time we're going to talk about piecewise functions. So let's get to it. So typically a function, right, like f of x is equal to 5/6 x minus 1 is just defined by one thing. In this case, it's 5/6 x minus 1. It's 5/6 because its rise is 5, the run is 6. And then it's minus 1 because the y-intercept is minus 1. So this is a linear function that we're looking at here. And that's normal stuff, right? What a piecewise function does is it breaks the domain of something up into a bunch of pieces. The domain of this function f is from -3, right? It starts here, to 9, right? Goes all the way to here. Those are terrible lines, but hopefully you get the idea, right? It's defined in this space here, horizontally. But a piecewise function is going to look to break that up and then define f in, I guess, in this particular case, 3 different pieces, right? You have a domain interval here, you have a domain interval here, and you have a domain interval here. Both of the piecewise functions that we're going to look at in this video today are defined in 3 different pieces, but you can have piecewise functions that are defined in 2 pieces. You can have piecewise functions that are defined in 50 or more different pieces. In this particular case, what I've done is I've broken up the domain into 3 intervals. We've got -3 inclusively to -1 exclusively, -1 to 4 both inclusive, and 4 to 9, where 4 is exclusive and 9 is inclusive. Okay, and what I'm going to do is I'm going to define only the first part of this function using 5/6 x minus 1, where -3 less than or equal to x less than -1, or that x is between -3 inclusively and -1 exclusively. And so this is a very standardized format, although typically where is kind of odd. Usually it's like if or something like that. I think I used if on the next one. Whatever. I could have put a comma or a semicolon. The point is, this function f is only defined by 5/6 x minus 1 on this interval only. Right? No other interval of this thing is going to be defined by that particular piece. So in the domain partition, right, this first one here, it's defined by this function in red. But let's define the second piece using something else. Okay, and then whatever that function would be placed here, and then the second domain interval would be placed after the where, or a comma, or if, or whatever it is that the textbook is using in that location. In this case, I went ahead and I defined it with -1x plus 4. So another linear function. It's got a slope of -1 and a y-intercept of 4. Both of its endpoints are closed in, right? Because it includes both of them. It's got the less than or equal to sign. And then the last domain piece, the 4 to 10, what the heck? 4 to 9. I went ahead and I defined it by this thing here. So 3/5 x minus 12/5, where x is between 4 and 9. Again, just ignore that. That's a 9 right there. All right? That's a piecewise function. That's pretty standardized, general example of piecewise function stuff. And what I want to do with the next example is really focus on 4 specific things. The first one is going to be to find the domain of the piecewise function. The second thing is I want to do some evaluating, so like plug in some stuff to the piecewise function. I want to graph it. And then we also want to discuss continuity. Now, continuity actually has a pretty complex definition that you don't learn until significantly later in your undergrad in math. But for right now, I think it's safe enough to just define it as, can you graph the function without lifting your pencil? And if this didn't exist, right, if this part didn't exist, then yes, I would say, I can draw this without lifting my pencil. Right, that's fine. The fact that this part does exist, though, you have to graph this, lift your pencil, go up here. There's a jump discontinuity that exists there. So this one would be no, right? This function's not continuous. So let's consider q of x. Okay, it's defined by 3 different functions on 3 different intervals of the Cartesian plane. We've got -4 to -2, -2 to 2, and 2 to 4. Right, those are the 3 different intervals for which we're going to be graphing. Or really doing all the things that I just mentioned in the previous slide. So first we want to find the domain, and in this class, and I'm not going to say that this is true everywhere. In fact, it's very much not true everywhere. But in this class, we are only going to focus on continuous domains. That's different than continuous functions. So not the can you graph without lifting your pencil thing. Continuous domain means every number in between the beginning and end, the lower bound and upper bound of the domain, is going to be included. So for us, we could really just look at where does the domain start and where does the domain end, and construct our domain that way. So in this case, if I'm going to define it using an interval, I would say the domain of Q is from -4 with an open parentheses to 4 with a square bracket. The next thing I want to do is evaluate. So we've got Q of -3, Q of 0, and Q of 2. And remember, evaluating is you're going to plug these numbers into the function. Now remember, it is a function. A piecewise functions fundamentally pass the vertical line test. So there is no, we're not going to take -3 and plug it into all three of these things. What you have to do is look at the domain intervals that exist and figure out which domain does -3 fall into, right? Is it the first one? Is it the second one? Is it the third one? Right? Well, -3 is definitely between -4 and -2, and so that's the domain that we're going to focus on, which means we can basically forget about these other functions, and for -3, Q of x is only defined by this thing. Q of x is equal to -1/2 x plus 1. So when you plug in 3, you're just plugging it into that thing, because that's how the function is defined for all the stuff that are between -4 and -2 exclusively. All right, so -3 times -1/2, that's +3/2. Then you're going to add 1 to that. You could turn this finding common denominator, that's 2/2. So you get 5/2 for that, and we're done. Now I invite you to pause the video here and see if you can figure out the other two. All right, welcome back. I'm going to assume you paused it, but if you didn't, I'm just going to go through the evaluations now. So 0 is in the second interval. It is between -2 and 2, and you'll notice that I wrote Q of 0 is equal to 2 already. And that's because when you go to plug in 0 for this thing, there's no x here. So it's like, well, what are you plugging it into? Well, nothing is, I guess, the answer here. You're not plugging it into anything. For all the values of the domain that are between -2 and +2, y, your Q of x, is just 2. So you're just going to have 2 as all the y values for the stuff that are between -2 and 2 when you plug it into Q of x. So that's 2. Now, when you're plugging it in 2, right, when we move to this one now, there's really two things you can consider, right? Because 2 shows up kind of in two domains, but remember, it's a function. So 2 only belongs to one of these intervals, and it's still the middle one, right? It's still this because it includes it. This second domain includes the upper bound 2. So you'll plug 2 into Q of x is equal to 2, right? It's just that piece, but it's just 2 again. So you just get 2 there. All right, now for graphing is a little bit more systematic. For me, let's take this thing in parts. Notice that all the pieces here are linear. -1/2 x plus 1, linear. Y is equal to 2, linear. Right? Y is equal to 2x minus 2, also linear. Everything's just linear. In this class, we will mostly just focus on linear equations for our piecewise functions. So you're allowed to do what I'm about to do here. But if you had a quadratic or something like that in the piecewise functions, then you may have to take a more detailed approach. Okay, but since these are lines, all I'm going to do is plug in the lower bound and upper bound to the function, and then use the appropriate endpoint, either open or closed. Looks like in this one, both of them will be open because there is no less than or equal to sign below them. And then just plot those points and connect them with a line. So if you plug -4 in for this x, you have -1/2 times -4, that's +2. And then you add 1 to it, so you get 3. So at the x value -4, you're getting the y value 3. So we put a point there. And it's open because it does not include it, right? Domain does not include it. Then I plug in -2, and -1/2 times -2 is 1. 1 plus 1 is 2. So we get another point here. And again, I'm just going to connect them with a line. Notice again that it is also an open dot because it does not include the less than or equal to sign. So that's it. That's the first part. All right, then we move to the next one. And I do the same thing. I'm going to plug -2 into Q of x is equal to 2 because we're pretending the other parts don't exist. And really, they don't for values that are between -2 and 2. Again, there's nothing to plug it into, though. So -2 just gives you a y value of 2. It's closed this time, so I'll just fill in the previously open dot. And then I'll also draw at 2, we get the y value 2. That is also closed here because it's less than or equal to, and so that's that piece. Finally, the last piece, again, plugging in the boundary, the endpoints, upper bound, lower bound of the domain interval into the 2x minus 2 function. then we get that when you plug in 2, you get 2 times 2, which is 4 minus 2, which is 2. That already exists as a filled in dot, right? So I'm just going to pick up where we left off essentially. So then let's move to the last endpoint. When you plug the last endpoint in, you get 4 times 2 is 8, minus 2 is 6. So that's why we've got a y value of 6 there. And that's also closed. Okay, and so then that's it, right? That's the piecewise function graph. That's what it looks like in this case. The question now is q of x continuous? Well, in this case, the answer is yes, because we can certainly draw this shape without lifting our pencil. Oh boy, that looks terrible. Just to pretend that's straight. So yes, right, the function would be continuous in this particular case. All right, and so that's everything I basically wanted to talk about in this video. If you guys have any questions, please drop a comment below or send me an email. Thanks a ton for watching, and I'll see you in the next one.